Here we want to solve this problem. We consider the motion of a projectile with the following initial conditions. So the coordinates of the projectile are all equal to 0, whereas the velocity is defined in terms of these components. Vy is equal to 0, Vz is equal to the mode of the velocity, the initial velocity v0 times the sine of the angle theta, which is an angle defined in the xz plane. We will see that later. And then we have Vx equal to V0 cosine theta. We have to consider the presence of the Coriolis force, and we have to find the deviation of the landing point due to Coriolis force in the second order of the perturbation theory with respect to omega, which is the angular velocity of the Earth. So our non-inertial frame of reference is the Earth, which has a certain angular velocity omega, and due to the presence of a non-inertial frame of reference, we have to consider the Coriolis force. The Coriolis force is the only non-inertial force that we are going to consider in this problem. Okay, so this is just an exercise, because otherwise, if we want to be more general, we should also consider the centrifugal force, for example. But we are only interested in the effects caused by the Coriolis force. The Coriolis acceleration, which I will call AC, is equal to twice the angular velocity omega cross product with the velocity. And in this case, this velocity v here is just the velocity of the projectile in the non-inertial frame of reference. If we call the mass of the projectile m, then we can write the equation of equilibrium in dynamics. So we have the mass of the projectile times the acceleration, the gravitational acceleration g, which is a force acting on the projectile, and then we have the Coriolis force, which is minus the mass of the projectile times the Coriolis acceleration. So we have 2 omega cross v, and then we also have the non-inertial force minus m times the acceleration of the projectile in this frame of reference, and this is equal to 0, the 0 vector. The acceleration here can also be rewritten as v dot, and therefore we can rewrite this equation by cancelling m, since it multiplies all those terms. V dot is equal to g plus 2v cross omega. Here I get a plus simply because I have switched the order between these two vectors, omega and v. So omega cross v can also be written as minus v cross omega, and therefore this minus sign will cancel this minus sign here. Now let's try to choose a frame of reference on Earth. So we have to consider the Earth. I'm going to make a sketch here. Let's assume that this is the vertical axis of the Earth. So here we have the North Pole, and the angular velocity moves around the North Pole. So it points along the North Pole. If we consider the omega vector, omega will be this vector here. It points to the North Pole. Then, if we consider here the center of the Earth, so we will assume that the Earth is spherical, and then at some latitude, we will have to consider the projectile. It will be located somewhere on the surface of the Earth, and the latitude is measured with respect to this horizontal line, which is perpendicular to the vertical line, of course, which corresponds to the vector omega. And this angle here, I will call it lambda. That's the latitude. And then along this line here, I will have the z-axis of our coordinate system, and I will choose as the x-axis an axis which points to the North Pole. So this is the x-axis. And of course, when we define the x-axis and the z-axis, we also have the y-axis somewhere here. So it's difficult to make a sketch, a precise sketch here, but you have to think of this in 3 dimensions. Now, if we want to write our vectors in this coordinate system, for g, it is very easy because this is simply 0, 0, minus g, where in this case g is just 9.8 meters per second squared. This is not a vector anymore, it's just a scalar. As we know, g is not really a constant in reality, but for this problem we are going to consider g as a constant. Now omega, which is this vertical vector, has two components, one along x and the other one along z. This angle here is 90 degrees minus lambda, and of course this is lambda. So omega can be written like this. It is simply the magnitude of the angular velocity, which is omega, times the cosine of lambda. And then we have 0 as the y coordinate. And then here we have omega sine lambda. Our velocity v has three components, vx, vy, vz, or if you want, we can call them x dot, y dot, z dot. So they are the derivatives of the three coordinates x, y, z, the derivatives with respect to time. We can calculate v cross omega, which is the cross product that appears here in the equation of motion, and we can calculate this by using a determinant I, j, k, x dot, y dot, z dot. Here we have omega cos lambda, 0 omega sine lambda. So this is a vector whose three components are omega sine lambda times y dot. This is the x component. Then in the y component we have omega cos lambda z dot minus omega sine lambda x dot, whereas the z component is minus omega cos lambda y dot. Now, since we have calculated this cross product, we also have g, we can write this equation here in three components. We have to write down the three components of that equation. So we have x double dot, because we have the derivative of v on the left, so we have x double dot equal to 2 omega sine lambda y dot. Then we have y double dot equal to 2 omega cosine lambda z dot minus 2 omega sine lambda x dot. Then we have z double dot equal to minus g minus 2 omega cosine lambda y dot. Now we can integrate these equations one time, then we will have to integrate it one more time, but first things first, let's take this first equation. We can rewrite that by integrating both sides, and in particular you can multiply by dt if you want. Dt, the differential of time, you multiply both sides by dt, and then you integrate like this. We integrate dx dot. So when you multiply x double dot by dt, you can rewrite that as dx dot, because dx dot over dt is equal to x double dot. And we integrate starting from the initial value of the velocity, the x component of the velocity, if you remember from the problem, it's v0 cosine theta, if you go back and check the problem statement. And we integrate all the way up to some generic value x dot. So this is the value that the x component of the velocity takes at a generic instant of time t. And this is equal to 2 omega sine lambda integral from 0, the initial value of the y coordinate. So here we have dy. We have to consider the initial value of the y coordinate, because when we multiply y dot by dt, we have dy. So this is the starting value for y, and we have to go to some generic value y. Then we do something similar for the second equation. I'm going to rewrite this as integral from 0 to y dot of dy dot, because the initial value of the y component of the velocity is 0. So we integrate from 0 to some generic value y dot. And this is equal to 2 omega cosine lambda. Integral from 0 to z dz, also z, the z component has a 0 initial value, minus 2 omega sine lambda, integral from 0 to x dx. And finally, let's consider the third equation. We integrate from v0 sine theta to z dot dz dot. The initial value of the z component of the velocity is v0 sine theta. So that's why I'm integrating from v0 sine theta. This is equal to minus g, and here we have integral from 0 to t dt minus 2 omega cosine lambda, integral from 0 to y dy. And now we have these three equations which we can easily integrate. Let me mention that the angle theta that you see in the three equations is this one. So if we have some starting velocity v0, which is a vector that lies in the xz plane, because it has a 0 component along y, but it has non-zero components along x and z. This angle here is theta. So the magnitude of v0 times the cosine of theta will give me the x component, and this is the one that you see here. And similarly for the y component, v0 sine theta. Now if you integrate these three equations, you can rewrite them like this. You have x dot minus v0 cosine theta from the first one, which is equal to 2 omega sine lambda times y. And then you have y dot equal to 2 omega cosine lambda z minus 2 omega sine lambda x, and then z dot minus v0 sine theta is equal to minus gt minus 2 omega cosine lambda y. Now you have a system of first order ordinary differential equations. And it can be solved. It can be solved quite easily, and I will show you how to write a formal solution to this system. We also have the initial conditions, so we can solve this system of differential equations. And also remember that in the end, we have to consider only the second order of our perturbation theory. So I will tell you something more later, but we will find a solution that depends on omega. We will find a solution that contains a function of omega. And essentially, we can simply find the general solution, which can be done here, and then we will truncate the solution to second order. There are several ways of solving this problem, but in this case, I have chosen the way I want to tackle this problem, and I will solve this problem by using matrices. So I will rewrite these equations in matrix form. On the left, I have a vector x dot, y dot, z dot, whereas on the right, I can rewrite a matrix 0, 2 omega sine lambda, 0, minus 2 omega sine lambda, 0, 2 omega cosine lambda, minus 2 omega cosine lambda, 0, 0, and here we have the vector x, y, z, plus Here we have v0 cosine theta, 0, v0 sine theta, minus gt. And this is the way I want to rewrite my system. We have a matrix here, which is anti-symmetric, but that doesn't really matter in this case. We are not interested in the form of the matrix. We just want to rewrite the system in this way. So we have this matrix that I can call A, and I will put a tilde here to denote that this is a matrix. We have a vector here, which is simply v0 plus the vector g times t, but for now we can simply call this b. And then here we have the vector x dot, and this one here is the vector x. So we have rewritten this system in this form. X dot, which is a function of time, of course, is equal to A, which is a matrix that does not depend on time, as you can see. It's a constant matrix, so we can put t here, then here we have x of t plus a vector b of t. So this vector depends on time because you see that here we have time. It's linear in time. And the differential system that we want to solve also has initial conditions. And if you recall, x of 0 was simply equal to the 0 vector. It's simply written in our initial problem statement. You can see it here. X of 0 is 0. The three coordinates at t equals 0, they are equal to 0. Now, formally, this system is exactly the same as an algebraic system that we usually write like this: x dot equal to a, x plus b, and in this case I'm just simply considering scalars, and x of 0 equal to 0. If we write the solution to this system, we can formally write also the solution to this system, and I will show you how. If we want to solve an ordinary differential equation like this, we can find first the integrating factor, the so-called integrating factor. We have to rewrite the system like this: x dot minus ax equal to b, and we take the term, the factor that multiplies x, we exponentiate it, so we take e to the minus a and then multiply by t. And remember that a is a constant, so we have to integrate minus a, and when we integrate minus a, we get minus a times t. If a depended on time, we would have to consider the integral here over time, but let's not overcomplicate things. A is a constant, so we can simply write this as e to the minus at. And then we multiply these terms by that factor, e to the minus at. So we have e to the minus at times x dot minus a times e to the minus at times x equal to b e to the minus at. And now you can see that the difference between these two terms can be written as the derivative with respect to time of e to the minus at times x, because the derivative of e to the minus at times x gives me these two terms, if you check. And now we can integrate both terms, this one and this one. So we can rewrite this as, so we integrate from 0 to t, and we get e to the minus at times x of t evaluated between 0 and t. And this is equal to integral from 0 to t of e to the minus at b dt. And therefore we can rewrite the solution like this. We have e to the minus at x of t minus x of 0, because of course when we set t equal to 0, this e to the minus at will become 1. And here we have integral from 0 to t e to the minus at b of t dt. Now remember that x of 0 is 0 in our case, so we can rewrite the solution like this. X of t equal to e to the at integral from 0 to t e to the minus at b of t dt. And formally, we can also rewrite this like this. X of t equal to integral from 0 to t. Then let's change the name of this variable inside the integral, because otherwise we might get confused. Let's call it tau. And let's put this e to the at inside the integral. So we have e to the at minus tau b of tau d tau. We can rewrite it like this. And if we want, we can also calculate this x of t at time tf instead of t. What is tf? tf is the final time where the projectile will touch the ground, let's say. So it will hit the ground. So the coordinate z of tf will be 0 by definition. We don't know yet what tf is. We have to calculate it. But this is the solution to the scalar differential equation. If we want the solution to our system of differential equations, of 3 differential equations, we can rewrite it simply by considering the solution to this one. We have the vector x of tf equal to the integral from 0 to tf of the exponential of the matrix A, and I will tell you more about this, times tf minus tau. And then here we have the vector b of tau d tau. How do you interpret the exponential of the matrix? The exponential of the matrix can be simply interpreted by considering the Taylor series of the exponential. We can simply write this as sum from 0 to infinity of the matrix A times the scalar tf minus tau raised to the power n, and then we divide by n factorial. If we interpret the exponential like this, well, it makes sense because we can calculate powers of matrices, but it is not so easy to understand how to calculate the exponential of a matrix. So if we interpret it like this, we can make sense out of the expression above. And oh, by the way, this can also be done in this case here, right? So it's as if we were reasoning by analogy. But if this guy right here solves the scalar differential equation, it is very intuitive to understand why this more complicated expression will solve the system of differential equations. So this is very important because we found the formal solution to the system. And we still have to work a little bit more on this. So if you recall, the matrix A here was this guy. And you can see that this matrix contains factors of 2 omega. And we can factor out 2 omega from the matrix. So we can rewrite the matrix A like this. Let me do it below. A can be written as 2 omega times another matrix, which is 0 sine lambda, 0 minus sine lambda, 0 cosine lambda, 0 minus cosine lambda, 0. And I can call this matrix capital lambda tilde. So formally, the solution x of tf can be rewritten like this. Integral from 0 to tf of e to the 2 omega lambda tf minus t, and then here the vector b of t can be written as v0 plus gt dt. This is formally our solution. Now, this vector equation here can be written in terms of three components. And you might wonder, how do we calculate TF? And I will show you how to do it formally from this equation, but intuitively it is quite easy to do it if you go back to the system that we wrote here, for example. Consider the z component of this system, and since omega is small because we are considering the angular velocity of the Earth, and the projectile will not be affected too much by the rotation of the Earth, because the motion of the projectile will take much less time than the Earth will take to rotate, let's say. So we might simply write this, and this is an approximation, okay? Later I will tell you how to do it more rigorously. I will show you how to do it from the solution to the system of differential equations, but now let me show you how to do it intuitively. If we neglect this term, because it multiplies omega, we get z dot minus v0 sine theta equal to minus gt. Now we can integrate both sides from 0 to the final time, and if we integrate z dot dt from 0 to the final time, we get z evaluated between 0 to tf. Then we have minus v0 sine theta tf, and this is equal to minus g tf squared over 2. But now when we evaluate z at time 0, we get 0, and also when we evaluate it at tf, we get 0. By definition, because the projectile will hit the ground. So this is 0. And from here we get an approximation of df. Df is approximately, here I will put equal to 2 v0 sine theta over g. And if you consider this one as the value for tf, you are going to make a very good approximation actually. Okay, so if you consider this value for tf, you can put it here in the integral if you want. So now I'm not going to do it, because even if we do not consider tf as a given value, we can obtain it from exactly this expression. Because remember that this expression has three components. And I will tell you now that from one of these three components, you will get the value of tf, especially from the third component, just like we did above. But in this case, this is a very general expression that will also consider higher order terms. So you will get some corrections to the value that we found above. Okay, so this is the reasoning. But since this is a very complicated expression, because here, remember that we have a series. We have a power series which depends on these matrices lambda, and we also have powers of omega. Since we want all the corrections up to second order, due to the Coriolis force, we can rewrite this exponential like this. We can take the first term, which is the identity matrix, and then we have plus 2 omega lambda times tf minus t, which is the first order, because you see that omega appears, and then we have plus this term squared, and then we have to divide by 2 factorial, so we get 2 omega squared lambda squared tf minus t squared. And we are going to stop at the second order. We don't want to consider corrections which are of higher order, even if in principle we could. So we can rewrite x of tf like this. Integral from 0 to tf, we have the identity matrix I plus 2 omega lambda tf minus t plus 2 omega squared lambda squared tf minus t squared times v0 plus gt dt. Now, x of tf can be written like this. We have two components, let's call them xf, yf, but the third component is 0. Also remember lambda. Lambda is this matrix 0 sine lambda. 0 minus sine lambda, 0 cosine lambda, minus cosine lambda, 0, 0. Then you have the vector v0, which is v0 cosine theta, 0, v0 sine theta. Then you also have the vector g, which is 0, 0 minus g. And if you didn't consider the perturbations, these terms here would be 0, this one and this one. So in the case of the unperturbed problem, which means that if we didn't consider the Coriolis force, we would have this problem here, x, let's call it x prime. So this prime here means that if we neglected the Coriolis force at time tf, this would be integral from 0 to tf of the matrix I, so this is the identity matrix. This would multiply v0 plus gt dt. And it's actually very easy to calculate because this is v0 tf plus g times tf squared over 2. And if we write it by using components, this would simply be v0 cosine theta tf 0, and the z component is v0 sine theta tf minus g tf squared over 2. Now, since we want to find the deviation of the projectile with respect to the position in which the projectile would hit the ground if there were no Coriolis force, we can also rewrite the problem like this. We can rewrite it as x of tf minus x prime of tf. And in this case, here we would find the deviation, and I will show you how. This is equal to integral from 0 to tf, and we have to simply eliminate the identity matrix from here, because the identity matrix will give us the solution to the problem if there were no Coriolis force. So if we subtract x prime tf, we would only find the deviation. That's what we are interested in. We want to find the deviation. So that's why I'm rewriting the problem in this form. And here I have 2 omega lambda tf minus t plus 2 omega squared lambda squared tf minus t squared, and this multiplies v0 plus gt dt. Now let's calculate the matrix lambda squared. We have to multiply these two matrices, 0 sine lambda, 0 minus sine lambda, 0 cosine lambda, 0 minus cosine lambda, 0. Here we have 0 sine lambda, 0 minus sine lambda, 0 cosine lambda, 0 minus cosine lambda, 0. And if you multiply these two matrices together, you get minus sine lambda squared, 0 sine lambda cosine lambda, 0 minus 1, 0 sine lambda cosine lambda, 0 minus cosine lambda squared. And now we can rewrite the problem. Also remember that x prime tf has these components. Okay, so we can rewrite the problem like this. On the left, let me thicken this pen here. We have xf minus v0 cosine theta Tf, and this first component, this x component here of xf minus x prime f, is the deviation that we have on x, so I can call it delta x. Then here we have yf minus 0, so the y component of f is already equal to the deviation delta y, because if there were no Coriolis force, the y component would be 0. So yf is equal to the deviation of y, which I call delta y. And then here we have minus v0 sine theta tf plus gtf squared over 2. So this is simply minus the z component of x prime of tf, because x of tf is 0. And we already know that this quantity here is equal to 0 if we didn't consider the Coriolis force. Because remember that Tf, if we neglect omega, which means that if we neglect the Coriolis force, was equal to 2v0 sine theta divided by g. And if you replace this value here, you get 0, right? But when we consider the Coriolis force, we cannot really say that this term here is 0, because there might be, as I said, other corrections. And let me tell you a little bit more about this in a few minutes. Now, we have to calculate an integral. Let me do it below. That's equal to integral from 0 to tf, and I'm going to rewrite the integral like this. So here, everything stays the same. I have 2 omega lambda tf minus t plus 2 omega squared lambda squared tf minus t squared times v0, and then I will rewrite gt as plus gtf minus gtf minus t. I will rewrite it like this, and then dt, because in this case it will be easier to calculate the integral, because the variable inside the integration here is tf minus t. If you take a look at it, tf minus t, whereas this is a constant and all other terms are constant. So you can easily carry out the integration. Let me do it here. We have minus 2 omega lambda tf minus t squared over 2 after integration minus 2 omega squared lambda squared tf minus t cubed over 3, and we have to evaluate it between 0 and tf, and then we multiply this by v0 plus gtf, because when we multiply this constant term by this, I simply have to integrate this term here and this term here. But I also have another term that I will rewrite below, which is due to the fact that when we multiply this by these terms, the integration will be different, but it will be very similar. So we have plus 2 omega lambda tf minus t cubed over 3 plus 2 omega squared lambda squared tf minus t to the fourth divided by 4, evaluated between 0 and tf, and then multiply by g. Now let's try to make our last efforts. We are reaching the solution, but just be patient a little bit. We have 2 omega lambda tf squared over 2. This will cancel this, plus 2/3 omega squared lambda squared tf cubed times v0 plus GTF plus, here we have minus 2 omega lambda TF cubed over 3 plus 2 omega squared lambda squared TF to the fourth divided by 4 times G. And now we have to rewrite this in matrix form, because remember that here we have matrices, so it will be more convenient to rewrite our problem in terms of matrices. Let me do it here. That's equal to, if you put these two terms together, the matrix lambda and also the matrix lambda squared multiplied by some constant terms, you can rewrite this first matrix that I'm going to underline in red like this. You have minus 2/3 omega squared TF cubed sine squared lambda. Let me separate the terms by using a grid. I have omega TF squared sine lambda. This is the term that we have in the first row and second column. And then we have 2/3 omega squared TF cubed sine lambda cosine lambda. Then here we have minus omega TF squared sine lambda. Here we have minus 2/3 omega squared TF cubed. And here we have omega TF squared cosine lambda. And here we have 2/3 omega squared TF cubed sine lambda cosine lambda. And then minus omega TF squared cosine lambda. And the last term is minus 2/3 omega squared TF cubed cosine squared lambda. This multiplies this vector here, which we have already written some time ago. We have V0 cosine theta 0, and then we have V0 sine theta minus GTF plus, and now let's make our last effort to rewrite this matrix here multiplied by this vector. It's very similar to the matrix above. Some constants will differ, but they will be very similar. So we have minus 1/2 omega squared TF to the fourth sine squared lambda. Then you have 2/3 omega TF cubed sine lambda. And then here you have 1/2 omega squared TF to the fourth sine lambda cosine lambda minus 2/3 omega TF cubed sine lambda minus 1/2 omega squared TF to the fourth 2/3 omega TF to the third cosine lambda. And here you have 1/2 omega squared TF to the fourth sine lambda cosine lambda minus 2/3 omega TF cubed cosine lambda. And here you have minus 1/2 omega squared TF to the fourth cosine squared lambda multiplied by 0, 0 minus G. Now we are ready to take the three components of our solution. Remember that we started from this vector here, which is the vector delta x, delta y, and this third component here that I'm not going to rewrite. We can take the three components of this system. So, for example, the first component can be obtained by multiplying this first row of the first matrix by the column of this vector, and then we add the first row of the second matrix multiplied by the column of the second vector. And we can get delta x in this way. So delta x, if you do the calculation, let me thicken this line. So delta x is equal to minus 2/3 omega squared tf cubed sine squared lambda v0 cosine theta plus 2/3 omega squared tf cubed sine lambda cosine lambda times v0 sine theta minus gtf. Then we have plus, let me do it here, minus 1/2 omega squared tf to the fourth sine lambda cosine lambda. So now you can see that the correction that we have in the x-coordinate of the landing point is proportional to omega squared. So if we didn't consider corrections above the first order, we would see that delta x would be 0. But as you can see, there are higher order corrections. Then we can also find delta y. Delta y is minus omega tf squared sine lambda v0 cosine theta plus omega tf squared cosine lambda v0 sine theta minus gtf plus 2/3 omega tf cubed cosine lambda times g. And in this case, for the correction to the y-coordinate, we can see that there is a proportionality with omega and not omega squared. So the deviation that we have on the y-coordinate is greater, is of a greater order of magnitude with respect to delta x. And finally, you also have the third equation, which is minus v0 sine theta tf plus gtf squared over 2. And we know that this is 0 if we neglected the Coriolis force. But in this case, this is equal to 2/3 omega squared tf cubed sine lambda cosine lambda v0 cosine theta minus 2/3 omega squared tf cubed cosine squared lambda times v0 sine theta minus gtf, and then we have plus 1/2 omega squared tf to the fourth power cosine squared lambda times g. And you can see here that the right hand side depends on omega squared, and of course it is of a smaller order of magnitude with respect to the left hand side. So we already make a very good approximation if we neglect or the second order terms with respect to what we have on the left hand side. But if you want it to be very precise, then you should solve this equation for tf, and you can, for example, simplify it a little bit because you can divide both sides by tf, and you will get the polynomial of third order. And you can find the solution to that. But of course, TF will depend on omega in that case. So you can find the solution that depends on omega, and therefore you can truncate that expression to some order of omega. But since we wanted to find the deviations delta x and delta y up to second order, we might already be satisfied with these solutions here by considering this left hand side here equal to 0. So in that case, TF was equal to 2v0 sine theta over g, a very good approximation. We have found the solution to this problem.